Greetings, psychology students. Welcome. The purpose of this video is to help you with the first half, the first two-thirds really, of your week 2 unit review. This is one of 4 videos that will be very helpful in completing the week 2 unit review. This video will cover the brain and the nervous system. The second video that I post will cover sensation and perception. The final 2 videos I will post will be crash course videos on the same 2 topics. My videos will take you directly through the week 2 unit review. So if you haven't already done so, pause this video and print that out and get it there next to you and follow along with me. So the first thing that we need to talk about is how we know what's inside the brain and what the functions of those structures are. And the earliest and easiest way to monitor the brain at work is the EEG, which stands for electroencephalogram. An electroencephalogram simply measures the electrical output of the brain. Remember that you have billions and billions of neurons, and electrical charges are occurring when these neurons fire, and the collective electrical impulses of all these neurons together can be measured by an EEG. You may remember when we studied sleep and dreams that long, slow waves called delta waves is what you produce when you're sleeping, and very short, fast, high frequency waves are what you produce when you're awake and focused. I gave you the memory trick, busy all the way down, B-A-T-D, beta, alpha, theta, delta. Beta, busy, fast, awake. Alpha, awake but relaxed. Theta, light sleep. Delta, deep sleep. And again, all these are measured using an EEG, an electroencephalogram. The second 2 are the MRI and the fMRI. An MRI, many of you have had them for sports injuries. They use magnetic fields and radio waves to take images of soft tissue in your body. More importantly for psychology and the way that we know so much about the function of the brain is the fMRI. The F stands for functional or functioning MRI, magnetic resonance imaging. The fMRI is able to show the brain as it performs a function. So somebody in an fMRI can be given various tasks, and then the images will show what part of the brain are active when they do those tasks. You can also take an image with a CT scan or a CAT scan. These are a series of X-rays. CT scans are associated with X-ray technology. And these are not useful in terms of learning so much about the brain, but rather in terms of specific injuries, as if someone perhaps came in with a head injury, might get a CAT scan. And then finally, the PET scan, P-E-T. This uses radioactive glucose substance that is ingested and then can very vividly be seen with this imaging technology. It gives an even clearer picture than an MRI or an fMRI, but who wants to be ingesting radioactive glucose just for the sake of scientific research? You may want to get one if you're about to have brain surgery and your doctor wants the best possible image and you're willing to ingest this. But in terms of all of these, the most important for you on the AP psychology exam is the fMRI, because this is how we know so much about the structure and function of the brain. We also know because of case studies, and the most famous case study in psychology is that of Phineas Gage. You remember Phineas? In the late 1800s, he was working on the railroad, and there was a small explosion causing a metal pipe to go through his jaw and out the front of his skull. And amazingly, it didn't kill him. And amazingly, he maintained most of his other functions, except his personality and his higher level thinking changed dramatically. And so as a result of this case study, we now have confirmed evidence that the prefrontal cortex, that is to say the front section of the brain, is mainly responsible for higher level thinking and personality. It certainly didn't kill him, so there's no life support going on here. He maintained his speech and his other cognitive functions. His memory was intact, so none of that was happening there. So this is what we learned from case studies. Now, let's look at the neuron. And I want to show you some very, very high level technology here, right? This is Boza technology. There it is. There's my neuron. And on this neuron, you're going to draw what I have drawn on my neuron. Let's start with, this is the front of the neuron, right? This is where all the action begins. It's the cell body, right? And soma is the prefix that we learn for body. And so it's sometimes called the soma. The cell body is the soma. And in the cell body, you can see here, is the nucleus. It's the cell body. Notice around the cell body, those extensions, they look like whiskers. Those are called dendrites. Dendrites. And at the end of those dendrites are very small openings that are called receptors, or sometimes they're called receptor sites. These receptor sites are like keyholes. And these keyholes are activated by specific molecular shapes of certain chemicals called neurotransmitters. Now, once the right neurotransmitter has activated the cell body by being received at the receptor site, then the neuron enters what's called action potential. It's just a fancy way of saying the neuron activates. It turns on. And it turns on for just a brief second. This is action potential, the brief second that a neuron fires. And when it fires, the neuron then sends an electrical message across this wire-looking structure called the axon. And the axon is coated in a mucus-type substance called myelin. It's a thick mucus substance that covers the axon. It's called myelin. It not only protects the axon, but it helps conduct the message from the cell body to the outside or the end of the neuron called the terminal. And so if you go to the far end, if you follow the axon then splits into branches, and these branches are called terminal branches. And at the end of those terminal branches, you see little bulbs, little round structures. Those are knobs, and they're called terminal knobs. Inside those terminal knobs, there are small sacs of chemicals called vesicles. Vesicles are small sacs of chemicals, and those chemicals are called, you guessed it, neurotransmitters. When the electrical impulse reaches those terminal knobs, the vesicles are released, and neurotransmitter then enters the space between this neuron and millions of other neurons, that space being known as the synapse or the synaptic gap. That neurotransmitter then is going to, guess what? Excite other neurons that are nearby. And this is how messages are sent from your brain to your body through the nervous system, and from your body to your brain through the nervous system. The structure of the neuron. Chemicals called neurotransmitters are received in the receptors, which are at the end of the dendrites. When that happens, the cell body turns on. It's called action potential. An electrical impulse travels across the axon. This electricity is created by the depolarization and the interaction of positively and negatively charged ions. When the electrical impulse is racing across the axon, that electricity is being created by the interaction of positive and negatively charged ions. As soon as this action potential is over, then there's repolarization, or just simply polarization. That is to say, those positive and negative ions once again get separated outside and inside, and the cell, the neuron, now goes from action potential back to resting potential. So resting potential, the cell is off. Action potential, the cell is on. A brief electrical impulse, also known as the neural impulse, is created by the depolarization. That means the interaction, the coming together of positively and negatively charged ions. How about that? Now, types of neurons. This structure that we looked at is the same for all neurons, but some neurons are very different from others. For example, in your brain and your spinal cord, you have very, very small neurons. These are the processors, the thinkers. They're called interneurons, I-N-T-E-R, interneurons. Throughout your body, in the peripheral nervous system, you have motor neurons, which your brain uses to send messages to move your body. And you have sensory neurons, which your body uses to send messages to your brain that has sensory information. Sensory neurons are also called afferent, A-F-F-E-R-E-N-T, afferent, A, admission. Motor neurons are sometimes called efferent, E-F-F-E-R-E-N-T, exit, A for admission, coming in towards the brain and the spinal cord, E for exit, going out, going away. These motor and sensory neurons never travel alone. They're too delicate. They're too fragile. Therefore, they travel in bundles that are coated in, guess what? Myelin, right? That thick mucousy substance. And a bundle of neurons coated in myelin is called a nerve. You have the motor nerve pathway, that is all the motor neurons traveling outside, away from the brain and the spinal cord to your body. And you have the sensory pathway, that is all the afferent neurons traveling in bundles, nerves, in from your senses to your brain and your spinal cord. The endocrine system, the word endocrine simply means hormones and glands. The most important gland is located in the center of your brain. It's called the pituitary gland, and it's often referred to as the master gland because it has control over pretty much all of your other glands, directing them when to secrete certain hormones. So the endocrine system just simply refers to glands and hormones. The pituitary gland, located in the center of your brain, which we'll get to in a minute, is the master gland. Let's go back to these neurotransmitters. The difference between a neurotransmitter and a hormone. Neurotransmitters work very quickly. They operate in the nervous system. They're produced by your body's nervous system, and they help facilitate messages throughout your body. These are neurotransmitters. They work quickly in the nervous system. Hormones work more slowly. You might argue more profoundly, in a more profound way. For example, testosterone and estrogen shape little boys and little girls into full-grown men and women over a period of just a few years. They make profound changes, but they operate slowly, and they operate in the bloodstream. So make sure you can distinguish between neurotransmitters, work quickly, nervous system. Hormones work slowly, perhaps more profoundly, in the bloodstream and produced by by glands in the body. There are certain neurotransmitters that you must know for the AP exam. This is not a comprehensive list of all the neurotransmitters. It's simply those, the greatest hits of the College Board. These are the ones that over the last 10, 15 years, they have tended to focus on the same 5, 6, 7 all-star neurotransmitters. Number 1, acetylcholine, also known as ACH, acetylcholine. Your body can't make any single movement without acetylcholine. It is the neurotransmitter that your brain uses to activate motor neurons that move your muscles. If acetylcholine is blocked for whatever reason, you would be paralyzed, right? Acetylcholine also has a secondary function, that is that it is involved with memory and learning. But that is not the primary function. If you're asked to use acetylcholine in a significant way on an FRQ, for example, stick with muscle movement. It enables the brain and the spinal cord to communicate movement commands to the body. The second one, dopamine, may be the most complicated of all of the neurotransmitters. By the way, here's a tip. Dopamine is one of the terms that you need to use in this week's practice FRQ. In that context, dopamine is associated with pleasure. When you laugh at a joke, hold hands with your boyfriend or girlfriend, when you enjoy the taste of food, your brain produces a certain amount of dopamine that is responsible for the pleasure that you get out of those activities. So dopamine is sometimes associated with pleasure. There are 2 other very important aspects of dopamine that the College Board tends to come back to every few years. Number 1, with regards to the disease called schizophrenia, there's a theory called the dopamine hypothesis. The dopamine hypothesis is that the cause of schizophrenia is a biogenetic cause, and that is that there's excess dopamine receptors in the brain. Dopamine is also responsible if you want to use your imagination, your creativity. So what if that aspect of your brain that could imagine things was out of your control? And that's what it would be like to have excess dopamine receptors, and that perhaps might be what it's like for some people who have schizophrenia. What about the absence or lack of dopamine activity? The lack of dopamine activity is associated with a disease called Parkinson's, specifically the inability to control fine muscle movement, like keeping your hands steady. So, therefore, the medicine that many people take for schizophrenia blocks dopamine receptors so that they can get their brain back to normal functioning. But guess what? It would cause their hands to shake because now they're going to be suffering from lack of dopamine, which is helpful for fine motor movement. So dopamine, pleasure, imagination, creativity, fine muscle motor control. Very complicated neurotransmitter and very likely to be on the AP exam somewhere. Another one that is very commonly asked about on the AP exam is serotonin. Serotonin is associated with moods. Specifically, people who suffer from major depression have lower levels of serotonin than people who aren't suffering from depression. Does this mean that depression is caused by low levels of serotonin? Perhaps, but it could also mean that when we are depressed, we produce less serotonin. Either way, it's the same principle. High serotonin, the presence of serotonin increases your mood. A lot of people take drugs for depression. These drugs are called antidepressants, but their real name is SSRI, specific serotonin reuptake inhibitors. And in a nutshell, what they do is they block your body's removal of serotonin after a neuron is fired so that you have more of your own serotonin, and therefore your mood tends to rise and your energy and your physical sense also tends to improve. The next one is norepinephrine. Norepinephrine is a neurotransmitter that's associated with several other hormones and chemicals that are produced when we get excited or scared, right? Remember the sympathetic nervous system, which we're about to talk about in just a moment. When you're nervous or excited or scared, your body produces chemicals, neurotransmitters, and hormones. This particular neurotransmitter, norepinephrine, is one of those. What does it do? It increases your heart rate, it increases your breathing, it makes you faster, it makes you stronger, it helps you focus. It's not a bad thing to be nervous before a race or a contest or even an exam. These hormones, these neurotransmitters, are wired into us through evolution probably to help us avoid danger, fight or flight, to reach our highest level of physical and mental potential. The next neurotransmitter is GABA, G-A-B-A, GABA. And when I taught it to you, I made a sheep sound. I said, GABA, GABA. And the reason I did that was to make a fool of myself. No, the reason I did that was because sheep are something that typically people count when they're trying to, that's right, go to sleep. So GABA is associated with sleep. Most neurotransmitters are excitatory, that is to say, they turn cells on. GABA, on the other hand, is inhibitory, that is to say, it blocks or prevents cells from being turned on. Therefore, when you're asleep, especially when you're in REM sleep and you're dreaming and you're being chased by bad guys and monsters, your body is incapable of movement. This is for your own protection. Again, probably an evolutionary characteristic that we've developed for our survival, for the good of our species. It's a good thing that we don't act out our dreams and we're incapable of doing it, in part because of the neurotransmitter GABA. Lastly, glutamate. What you're hoping is that all of this information, when you sit down to take the exam in May, has stuck to your brain like, that's right, glue. So glutamate is a neurotransmitter that's associated with memory, forming long-term memories. In order to memorize this information, in order to store this knowledge for future use, your brain is going to take advantage of a neurotransmitter called glutamate. You want this information to stick to your brain like glue. Now let's look at the nervous system. And once again, we're going to employ Boza's high level of technology. Oh, there it is right there. That is just extraordinary. The nervous system consists of two main divisions. That is the central nervous system, the brain, and the spinal cord. They are really one. The spinal cord is an extension of your brain. It utilizes the same kinds of neurons. Remember, we learned them. They're called interneurons, processors. Your spinal cord, by the way, can think even faster than your brain, or at least parts of your brain, at least the higher level parts. A reflex, remember the reflex arc. You jump before your brain can process that you've seen a snake. How? Because the information went through your spinal cord first, and your spinal cord knew that there was danger and sent a message to your body to freeze or jump as the information was still being sent to your brain for conscious processing. So the central nervous system is the brain and the spinal cord, interneurons. PNS stands for peripheral nervous system. That is all the motor and sensory neurons that we talked about. The peripheral nervous system is also divided into two divisions. The somatic, the one I'm using right now to move my hand up and down, voluntary movements, anything you do consciously, is somatic. Remember the prefix soma means body. Moving your body voluntarily requires the somatic nervous system. But your body and my body are also doing a number of things right now that we're not consciously aware of. This is the autonomic. conveniently named because it sounds like the word automatic, but these things, these processes are happening automatically. Glands and organs, your lungs, your heart are all working autonomically. Lastly, the autonomic nervous system is finally subdivided into the sympathetic, that is to say, the arousing, exciting part of your nervous system, and the parasympathetic, the calming, restorative part of your nervous system. So let's move on then to the actual brain, right? Always think of the brain in 3 levels, right? The lower, the middle, and the upper levels. The lower, middle, and upper levels. The lower level of your brain, right above the spinal cord, is sometimes called either the brain stem or the hind brain. The brain stem or the hind brain. In the brain stem, you have mostly life support, autonomic, that is unconscious, life support, breathing, heart rate. The medulla is the structure in the brain stem that is controlling most of this autonomic life support functioning. The pons relay information from the lower to the upper brain, and therefore they're very active during dreaming, because that's what dreams are. Dreams are just a series of random images and thoughts that go back and forth from the lower to the upper brain. The pons. The reticular formation. Reticular formation is your body's alarm. It is, again, an evolutionary characteristic that we have, that certain sounds are going to get our attention, right? The sound of something moving in the bushes, the sound of something behind us when we're walking in the darkness, the sound of a baby crying to a newborn mother even though she's sound asleep. Somehow these faint sounds are going to get our brain's attention even when there's lots of other commotion, because of the reticular formation. Lastly, in the brainstem, I don't see it listed here on your review, my apology, but very important is the cerebellum. The cerebellum. All you athletes out there, you practice. And why do you practice your golf swing? Why do you practice your throwing and your shooting? Because the more you do it, the less conscious you have to be of doing it in the game. Your brain, your upper level brain, is not going to do it for you during the game. Hopefully your cerebellum is going to do these unconscious motor movements so that your upper brain can think strategy. If you're dancing with your upper brain, you're a really bad dancer. If you're playing sports with your upper brain, you're a really klutzy athlete. High-level athletes, high-level artistic dancers and musicians are playing their instruments, moving their bodies mostly with the cerebellum, unconsciously. The lower part of your brain is not only unconscious, but it's much faster than the upper part of your brain. The middle part of your brain, the limbic system, crazy town. This is the part of our brain that causes us to make so many bad choices, right? Because the middle part of your brain is responsible for urges and appetites. And if the middle part of your brain, the limbic system, if the nickname is going to be Crazy Town, who's the mayor of Crazy Town? The mayor of Crazy Town is the hypothalamus. Because the hypothalamus is going to control, it's like a thermostat that each person has that dictates how much food, how much sex, how much activity is going to be satisfying for them. Have you noticed that people differ in terms of their appetites for all these things? And that's because of the hypothalamus. Everybody's hypothalamus is like the thermostat in everyone's particular home. It's set at a certain level. Hypo means below, so the hypothalamus is below the thalamus. The thalamus is a relatively boring structure. It's simply a relay for all of your senses except, which one? Do you remember? That's right, class. Good. Smell. Smell goes directly to the front of the brain, but all other senses, all the other 4, go through the middle of the brain, through the thalamus, before they reach the cortex, the upper level of the brain. The hippocampus. Why is the hippo on campus? We know why the hippo's on campus, for the same reason that we would be if we were allowed, and that is to learn new things. The hippocampus, therefore, is responsible for processing new long-term memories. If your hippocampus is damaged, for example, you won't be able to store any new long-term memories. You would suffer from something called anterograde amnesia, the inability to store new memories. What neurotransmitter is going to be involved? That's right. You remember from about 10 minutes ago, glutamate, right? Glutamate is going to be implicated in this process of storing new memories in the hypothalamus. We've already talked about the pituitary gland. That's the master gland. And lastly, I'm not going to scream because my wife's in the house and I don't want to freak her out. But if I would scream, what word would I scream? Amygdala! The amygdala are two pea-sized structures, each on either side of the brain, the left and the right hemisphere in the middle, and they're associated with strong emotions, specifically the emotion of fear. That's right. Finally, let's go to the top of the brain. So the brainstem, the limbic system, and now the cerebrum. The top thick section of your brain is the cerebrum, but the only part we're really interested in is the outer quarter-inch layer. The outer quarter-inch layer, got a fresh haircut. The outer quarter-inch layer called the cortex. And the cortex is going to be made up of 4 lobes. 8 when you count that each lobe has a left and a right hemisphere. So I've got my left and right frontal lobes, left and right parietal lobes, my left and right occipital lobes, and my left and right temporal lobes. What do you need to know about these 4 lobes? Really very little, right? 1 or 2 things about each lobe, and then we're pretty close to being done. We'll just talk about the 2 sides of the brain and we're done. The frontal lobes. What's important about the frontal lobes? Well, remember the story of Phineas Gage. We know from research, from fMRIs, and from case studies that the front of the front, the prefrontal cortex, the front of the front, prefrontal cortex, is where you have your higher level thinking. This is your ethical self, your moral self. This is your unique personality that is you, right? The frontal lobe. In the back of the frontal lobe, right in the back of the frontal lobe, you have a strip, a left and a right motor cortex. The left motor cortex moves everything on the right side of your body, and the right motor cortex moves everything on the left side of your body. So what do you need to know about the frontal lobe? Prefrontal lobe, higher level thinking, motor cortex, movement. Right behind the motor cortex is obviously the parietal lobe, but in the front of the parietal lobe, so parallel, right next to the motor cortex on either side, you have the left and right sensory cortex, sometimes called soma, as in body, somasensory or somatosensory cortex. This is where you feel things. This is body feeling, somasensory, body feeling. Everything that touches the right side of my body is processed in my left sensory cortex, and vice versa. Everything that touches the left side of my body is processed in the right sensory cortex. That's really all you need to know about the parietal lobe. Likewise, all you need to know about the occipital lobes in the back of your head is that this is where the visual cortex is. You want somebody to see stars, hit them in the back of the head, because that's where they're processing vision. They're more likely to have visual problems if you hit them in the back of the head than in the front of the head, right over the eyeballs, right? The occipital lobe, this is where vision is being processed. Finally, the temporal lobes, right? Left and right temporal lobes. This is where we're processing hearing. This is where the auditory cortex is. There are a couple of special areas in the left hemisphere One of them is known as Broca's area, B-R-O-C-C-A. It's named after the doctor who discovered it, Broca. And Broca's area, conveniently, is in the left motor cortex, and it moves your mouth to make speech. And the reason I said conveniently is because most of you know enough Spanish that you know boca means mouth, and Broca sounds like boca, so moving the mouth. Also on the left hemisphere, but in the temporal lobe, is Wernicke's area. Wernicke's area is where we process the meaning of language. For you to understand what I'm saying right now requires the use of Wernicke's area. There are numerous other association areas all over the brain, but for some reason the College Board has fixated on those two over the last decade. And so that's why I'm highlighting them for you. Lastly, finally, remember that your brain has two hemispheres, and they are connected by tissue called the corpus callosum. The corpus callosum is the tissue that connects the left and the right hemisphere. Believe it or not, there are some people walking around who have had their corpus callosum severed, that is to say, cut in half, where the right and left sides of the brain can no longer communicate. The reason for this drastic procedure is to eliminate very extreme epileptic seizures. If people have very severe epileptic seizures and nothing else has helped them, and they are desperate for another procedure, sometimes doctors will sever the corpus callosum, and it prevents messages from being stuck in between the two hemispheres, which can result in some very severe seizures with epilepsy. What is the difference between the left and the right hemisphere? Well, remember we just talked about the left hemisphere having Broca's area and Wernicke's area. This is no accident. The left side of your brain is the language side of your brain. It's also the logic side of your brain. Most everything you do for a grade in school is left-brained. Math, reading, right? All that is left-brained. What does the right brain specialize in? The right hemisphere specializes in spatial awareness. That is to say, creating cognitive maps, being able to close your eyes and imagine where things are. Facial recognition, the ability to recognize the names and identities of people when you see their face, that's happening on the right side of the brain. The right side of the brain also tends to have more artistic and emotional qualities. Are they really that completely different? No. Can each hemisphere take over for deficiencies in the other half? Of course they can. And the last term I'm going to go over with you is the term neuroplasticity. And that is to say that your brain has an amazing capacity to develop a way to overcome any kind of damage or anything that incapacitates a particular region of the brain. For example, if you were to damage Broca's area, it would definitely impede your ability to speak. But slowly, over time, with therapy, other parts of your brain could learn to take that function. This process is called neuroplasticity. The brain is far more complicated than I just made it sound. I just gave you the most basic, watered-down College Board version that will help you to be successful on the exam. I hope that this video has helped you complete the assignment, or at least the first 2/3 of the assignment. Once again, there'll be another video posted for sensation and perception, as well as a couple crash course videos that you'll need to complete this weekly assignment in total. Peace.